welcome to the morning session of the second year workshop. It's a pleasure to have Aaron and Sam. They're going to tell us about Pseudo Calibration. It's a new technique in Fourier lower bounds expressives.
Good morning, everyone. Thank you very much for inviting me. It's a pleasure to be back here. Today we'll talk about Pseudo Calibration, a technique that was developed for the recent almost squares lower bound for planted clique, and in fact, much of this work was done in these very halls. So, what is Pseudo Calibration and when can it be applied? Well, let me start with the second question first. So we can apply it on planted problems, where for planted problems, planted problems ask, can we distinguish, given a single sample, can we distinguish with high probability between a random distribution and a planted distribution?
I guess the answer is it depends.
One more phrase, computationally efficiently. And yeah, it depends on the problem. And in particular, for most of the talk, we'll focus on low degree sum of squares. Okay, so let me give some examples for planted problems. So one example is the planted clique problem, which we worked on extensively. So here, for a random distribution, we take gn 1/2, just a random graph where each edge is there or not there with probability 1/2. And then for a planned distribution, so most of it is still random, but we also have a planted clique. What this means is, so we'll take we'll put each vertex in the clique with probability k over n, where k is a parameter which is the expected size of the clique. And then, like, all the vertices which you've chosen to put in the planted clique, we'll make them all adjacent to each other, so to plant a clique there. So it's mostly random, but there's a planted clique. And a second example is random 3 XOR. So in the random distribution, we'll have m random parity equations. say like x1 plus x2 plus x7 equals 0 mod 2, x2 plus x4 plus x5 equals 1 mod 2. And then in the plan distribution,
Could you write way bigger than
Yeah,
that?
maybe you could pull out with a board from this side and or erase some stuff. Yeah.
okay, yeah, I guess I'll erase.
Or you're empty.
Yeah, that one has some hidden stuff. This one doesn't.
Yeah, I'll erase this for now. And then for the planar distribution, so we'll start with so I'll start with a random solution x naught, and I want to do the n, and then we'll choose m constraints, or m parity equations at random. But under the condition that they agree with our chosen solution x naught.
So you always choose 3 variables, and then you see if they add up to 0 or to 1.
Yeah, exactly. So like you choose 3 variables, see under x naught, do they add, are they 0 or 1 mod 2, and then like you have that be your equation. Okay, and now, so now what does pseudo calibration do? So pseudo calibration is the technique for showing these distributions are hard to distinguish. And this gives us so this gives us integrality gaps for. So for much of the talk, we'll focus on sum of squares. But there's a good chance that the techniques here. Is this too low? Probably.
It's okay. We have TVs.
So there's a good chance that the technique can be applied for other linear programs and semi-definite programs. Okay, so now what kind of what kind of results can we show with pseudo calibration? So here I'll start with a recent almost tight lower bound for a planar clique, which says that the integrality gap on random graphs is almost the square root of n. So let me make a few remarks on this. So
is this n or d divided by log n?
D divided by log n, where d is the degree of the sum of squares. So the general idea is that as d gets higher, the sum of squares hierarchy performs better, and this says this is the trade-off which we prove. Although finding the exact trade-off is still open.
So is this O means at least or at most?
O is a constant times the square root of d over log n.
Okay.
So in particular, at d equals log n, then there's no longer a lower bound, which is good because, as I'll describe now, at d equals log n, constant times log n, the problem is easily solved. So yeah, as I was going to say here, both d equals O of log n and the square root of n are tight. So the reasons for this, so if you look at a random graph with high probability, the largest clique in a random graph has size of almost exactly 2 log n. So if d is much bigger than 2 log n, degree d SoS can certify yeah, I should say for these that there's an input graph G. Can certify the input graph G has no larger clique. And this is essentially by brute force search. And second, so even degree 2 SoS can certify G has no clique. All these are probabilistic statements, but has no clique of size more than about square root of n. And this is by looking at eigenvalues of the adjacency matrix. And yeah, this is essentially the spectral algorithm of AKS 98.
So in the planted clique, you have the parameter k, which determined how large your clique would be.
Yeah.
So you would have in your planted clique, the clique to be larger than log n?
Oh yeah, a good question. Yes, here we'll say that k is much bigger than 2 log n because if it was smaller, you couldn't, information theoretically, you couldn't distinguish it from what's already there. And as I'm discussing now, we'll want k to be much less than square root of n because at square root of n, like a spectral algorithm can certify there's no such clique. So, and what we're showing is like up to almost square root of n, sum of squares fails to certify this and has like a large, so it has this integrality gap of almost a square root of n.
So if there's a clique of size larger than root of n, then a degree 2 SoS can certify it.
Can find it, yes. And this is essentially the spectral algorithm of AKS 98. Okay, are there further questions before I continue? All right. And the last remark I'll make about this is that it's not easy. It's not easy to prove the lower bound. In particular, before pseudo calibration, previous approaches we were stuck at about n to the omega 1 over d. Sorry, not omega. Oh, n to the O of 1 over d. Okay, and now for So for random 3 XOR, a classic result of Grigoriev says that as long as the number of clauses isn't too large, then even very high degree sum of squares thinks that they're all solvable. And for this result, you don't need pseudo calibration. That said, so in recent work inspired by pseudo calibration, so KM, Cathari, Mori, O'Donnell, and Whitmer. So they proved tight SoS lower bounds for all average case CSPs. Okay, yeah. So these are the kind of results that we can show with pseudo calibration. So now let me describe degree D sum of squares. Although actually, but before I do that, yeah. So now let me describe degree D as sum of squares. Here, we won't describe it in general. But we'll describe it for max clique and give the general ideas for how you would apply it more generally. Okay, so for max clique, let's actually start with. So we have an input graph G. So let's start with the basic SDP, which corresponds to degree 2 SoS. So in the intended solution, we'll want xi equals 1 if I is in the clique and 0 otherwise. And we'll also want that mij equals xi times xj. Now, of course, we'll have to relax this. So what kind of things can we say? So xi squared is going to be 0 or 1, but all we can really say there is that for all I, mii is at most 1. Well, we want this to be a clique, so we better have that mij is 0 whenever I is not adjacent to j. And third, so here, like in the intended solution, M is a rank 1 PSD matrix. So all we can really constraint for a semi-definite program is to say that M should be PSD. And the objective value, so the objective function, we're trying to maximize sum over I of mii. So this would be a basic SDP for maximum clique. So now degree D sum of squares. So here we'll we'll do something similar, but we'll have a large matrix. And now it'll be indexed by subsets, ST, of size at most d over 2. Yeah, so here I should give a definition. So we'll define xv to be the product of I and v of xi. So now, similarly to before, so in our intended solution, so we want xi equals 1 if I is, same as before, we want xi equals 1 if I is in the clique, 0 otherwise. In particular, xs is equal to 1 if f is a subset of the clique and 0 otherwise. And MST, we want it to be the product of xs times xt. And now for relaxation. So here, so we'll need a normalization condition. We better have that MST is 0 if S union T is not a clique. We'll have a bunch of symmetry constraints. So MS prime T prime should equal MST if these correspond to the same subset. So S prime union T prime equals S union T. Again, we'll have that M should be PSD. And again, but again, we'll have exactly the same objective function. We're trying to maximize sum over I of MII.
Sorry, can you say in the first one why the identity matrix is not a feasible solution to this program that you wrote down?
Let's see. Actually, when
the rule for the empty set.
Okay. I think you're right that actually. Thank you. I think that there was a bug that I do need a row for the empty set. That I think again I'd need empty set equals 1 empty set I equals MII.
So maybe you said it implicitly, or so your input graph is G, and on your second degree D SoS, I see how your matrix M, your condition depends on G, because you say S union T better be a clique.
Yes.
But on your first SDP, I don't see that.
Oh, it's right here. Like if F in G, like this is so like the, if I is not. So here's the same thing, just with a single I and J.
This I always thought it I X J, but you meant I not adjacent to J. Okay.
Yes. Oh yeah. This here was not adjacent. Okay, but you make a good point. Let me think about this question and perhaps get back to you at the end. Because right now, let me. For now, let me talk about pseudo calibration. So what pseudo calibration does is it gives, it's a technique for finding a feasible solution M. It's to the degree the degree D SoS semi-definite program, which I've described here. Oh, actually, before that, actually, maybe let me. So I'd give some general ideas for how you'd write the degree sum of squares in general. So. Generally, you'll have a large matrix M indexed by monomials of degree at most d over 2. You'll have many constraints. Which you can derive from the intended solution. And you'll have a lot of symmetry constraints saying that entries corresponding to the same monomial should have the same value. Okay, yeah. So this is a flavor for how you would how you'd get the degree D sum of squares program more generally. Yeah, but now let me return to pseudo calibration. So pseudo calibration is a technique for finding a feasible solution to this degree D sum of squares STP. Okay, so this. This will seem somewhat out of the blue, but we'll give a motivation for it soon. So here we'll start with the following the following function for taking a input graph or an input I and obtaining a matrix. We'll define lambda st of an input I to be the relative density of I, which is equal to the probability in a planted distribution, in the planted distribution of obtaining I, divided by the probability in the random distribution of obtaining I. And now here, so I should have noted this earlier, but the planted distribution is actually a joint distribution on an input I and a solution x. So what we'll have here is we'll have the expected value, given that the input was I, of xs times xt. Okay, so I guess I'll first start with some observations about this function. So the key observation is that it satisfies everything except normalization. Okay, so why is this true? So the reason is that it's either 0 if the input is not in the planned distribution, or it's a constant time, well, a large constant, very large constant, times a distribution over actual solutions, like actual intended solutions. And a key idea is that by design, intended solutions satisfy the constraints. So it automatically pointwise satisfies all the constraints except normalization. However, the problem is that this function here fails normalization badly. So in particular, this relative density mu I, it's almost always 0. And then on graphs which are part of the planned distribution, it's exponentially large. So it's badly behaved. So what can we do?
Can you say just again, so probability planted I, how do I interpret that again? So it's the probability that I is in the planted distribution?
So the planned distribution is a distribution on inputs. So it says like on graphs or more generally on inputs. And so what it's saying, so it gives it, so each input has some probability. Yeah, and the idea is so the random distribution takes every input with equal probability. The planned distribution will have much higher weight on the inputs which actually have a solution.
And then the x conditioned on I is, so assuming that you are planted, then x is the key? So
yeah, actually it's a joint the planned distribution is a joint distribution on inputs and solutions. So I guess it's possible, though it turns out like not pretty rare that there could be multiple x's. But this is just saying given that the input is I, take the expected value over the corresponding x's of xs times xt.
Yeah. Okay. So this is just the moments of the actual.
Yes.
What is everything?
Everything would be these three conditions here.
Oh, okay. Okay.
Alright, yeah, so yeah, I'll say the key idea and then hand things over to my co-speaker Sam. So okay, so lambda here is badly behaved. So how might we fix that? So the key idea is we'll we'll only take the low degree part of lambda. And we'll hope this smooths lambda out. And Sam will make this more precise in the second half of the talk. For now, are there any questions before? Oh.
Yes. So you said there's an integrality gap for the degree D SOS. Are you talking about the specific degree D SOS that you gave us here, or would that also apply to if I add some more conditions?
I'm applying to the specific degree D SOS which I gave here.
All right. Thanks, Aaron. Am I on?
No,
I have my own. He just has to unmute me. OK, thanks a lot. OK, so thank you, Aaron. I want since we've gotten our key definition up, and I'm going to spend most of the last 20 minutes discussing it. But before I do, I want to spend a couple of minutes on just the global picture here, because we've gotten sort of detailed. So just to refresh ourselves, the project is to understand inequality gaps for very strong semi-definite programming relaxations. We thought about SDPs from the sum of squares hierarchy, but you could imagine these ideas also working for strong linear programs or even other kinds of SDPs. And the main difficulty in producing inequality gaps for these semi-definite programs is that one has to construct these moment matrices. These are large positive semi-definite matrices that obey very complicated linear constraints. So this is, we've seen some explicit families of rather complicated linear constraints. As we've noted, you could even imagine adding more of them. And in the before pseudo-calibration era, like the project of constructing such a moment matrix was some very difficult creative task. It was not at all clear how you should choose the entries of this matrix. If you want to construct a moment matrix that's supposed to if you want a generic construction that was supposed to sort of work for a random graph, it was really not clear how you should have the entries of this moment matrix depend on a random input. And the point of pseudo-calibration is that it gives you totally mechanically a candidate moment matrix to analyze to prove an inequality gap like either of these, or for a variety of other problems. Okay, so you specify a family of random instances that you want to prove an inequality gap for. You specify some planted distribution of instances that have a large integral solution with a large objective value. So here, the planted distribution we've been talking about is this planted clique thing. The graphs in this planted clique distribution, they have a large clique, a large integral solution. And pseudo-calibration takes these things and mechanically tells you a candidate moment matrix construction to prove an inequality gap. Analyzing that candidate moment matrix might be very difficult. Right now we have a few techniques for it. It's not clear we have the simplest or the correct proofs for these yet. Although we can, in specific cases, prove results like this. But the point is that this construction would have required a great deal of creativity, and it now becomes mechanical. OK, so if there are questions about the global picture, I'd be happy to discuss it. Otherwise, I'm going to return to specifics about how you do this mechanical construction of a candidate moment matrix. OK, cool. So Aaron set us up with this function lambda. Lambda, let's just sanity check here. Lambda sort of has the right types. It takes an instance of your problem, and for the remainder of the talk, I'm just going to think about planted clique, and it should be understood that these ideas are quite generic. They can apply to CSPs. They can apply to a number of sort of machine learning-y problems. Lambda, it takes an input to your problem, in our case a graph, and it produces an n to the d by n to the d matrix, so lives in the space of moment matrices. And it point-wise satisfies many of the constraints of the sum of squares SDP. So this is great. It's always a PSD matrix. It point-wise satisfies most of linear constraints. But the main problem is that this function is ridiculously spiky, right? For most graphs, it's 0. And for a very small fraction of graphs, exponentially few, it's got a huge value, right? Because it's just focused on graphs that actually have large integral solutions. And now the idea is that our candidate moment matrix will be the projection of this function lambda to low-degree polynomials in the graph G. Okay, so I'm going to make this precise in a second, but what is a low-degree polynomial in a graph? Well, think of a graph as being an n by n adjacency matrix of zeros and ones, and then you could imagine evaluating a low-degree polynomial in those variables. But in lambda itself is an extremely high-degree polynomial, but it has a low-degree part, and that's what we're going to use as our candidate moment matrix. So I'm going to do some fairly brief discussion of this. So the pseudo-calibrated moment matrix comes with some parameter capital D. D is the degree of polynomials that will project this function lambda to. So it's going to be, it tells me a value for every one of the variables in my sum of squares SDP. In fact, it tells me how that should depend on a graph G. So here we were talking about generic instances, but I'm just going to focus on planted cliques. So G's are graphs. And it says that what you should do is just evaluate the low degree projection of lambda on G. And to define this, I'm going to give you some very brief refresher on discrete Fourier analysis, and then we're going to derive a very explicit expression for this moment matrix M, for the entries of this moment matrix M. Okay, so actually, before I do that, let me note that if you take one thing away from the talk, it's this definition and the fact that generically this definition captures, up to some contention among the authors of these papers, the construction that's used to prove SDP, to sum of squares lower bounds for CSPs, the best known such lower bounds. It captures the construction used to prove lower bounds for planted clique. It captures the best known lower bounds for a number of machine learning-y problems, component analysis style problems. So somehow this unifies many existing sum of squares SDP lower bound constructions. Okay, so let me do some brief refresher on discrete Fourier analysis so we can talk about what it means to project this function lambda to low degree polynomials. And then we'll wrap up the talk by getting our hands a little bit dirty and getting some very explicit expression for this thing that, if you want to try it for yourself, maybe it's a calculation you can take home with you. Okay, so a brief refresher on discrete Fourier analysis. We'll be interested in real valued functions on the n-dimensional hypercube, where I'm going to write capital N, so not to be confused with the little n that we were talking about over here. And I'm going to think of this hypercube as being on plus minus 1. And it's a classic theorem that every such function f can be expressed as a degree at most 2 times capital N polynomial. Capital N polynomial. Degree capital N polynomial. To see how this expression works, the key ideas are that there exists a simple inner product of functions from the hypercube to R, and that with respect to this inner product, there's a simple orthonormal basis of functions called the Fourier characters. So we'll just see those very quickly. So if f and g are two functions like this, the inner product of f and g is the expectation over a random x from the capital N dimensional hypercube, f of x times g of x. And there is there's an orthonormal basis of functions chi alpha, where alphas are subsets of the coordinates. And we'll see an explicit expression for what chi alphas are. Well, it's kind of floppy writing.
Aren't these just the monomials?
These are just the monomials, exactly. So they're just the monomials of plus minus 1. So it's classical that if I take chi alpha of x to be equal to just the product over the coordinates in alpha of xi, then these are orthogonal functions with respect to this inner product, and every function f is equal, has an expansion in terms of these functions, where f hat alphas are real numbers. And these Fourier coefficients f hat alpha are given by the inner product of f chi alpha, which is just equal to the expectation under a random point on the hypercube, x minus 1 to the n, f of x chi alpha of x. OK, there's our refresher. And the whole reason to describe this is because secretly, random graphs, which we were talking about up till now, random graphs are just random samples from the little n choose 2 dimensional hypercube. Right? So back to us in G n half. G n half, the Erdős-Rényi distribution, is the uniform distribution on the capital N is little n choose 2 dimensional hypercube. So now the coordinates of this hypercube are pairs of indices up from 1 up to little n, right? And the distribution G n half is just a random sample from this hypercube.
Question?
Yes?
For my sanity, so this MSTG is not yet normalized correctly, is it?
Which thing? Sorry?
The actual pseudo-calibrated moment matrix. It's not like normalized correctly yet, or is it?
No, I think it should be normalized correctly.
Because we were saying, okay, so I'm
So-
probably just missing something.
No, go ahead.
Previously, we were saying it satisfies everything except for normalization.
Exactly. So the reason that it doesn't satisfy normalization is because there's this function sitting out here that's, yeah?
Wasn't defined in that context. I think.
Oh.
The fact that it's the expectation of the pseudo expectation of 1 is 1.
Yeah.
You want to say that that's a normalization.
Yeah. So I think it was defined. But OK, so just to be clear about what normalization means, let's have a parenthetical remark here. So normalization, I'll just stand right in front of what I'm writing. Normalization is this constraint that the upper left entry of the moment matrix is equal to 1, right? OK, so why wasn't this satisfied? Well, the upper left entry of this matrix, well, if I put empty set here, then this is 1. But I multiplied by this number, which is potentially enormous. And the point is going to be that the only the high degree part of this function mu is able to be spiky like this. And when I truncate it to low degree, it'll smooth out this spike. And the whole thing will turn, what will turn out to happen is that this entry is very close to 1.
Or maybe just that, the empty set is kind of like a low degree, the lowest possible degree.
So this is good question, good point. So it is the lowest possible degree over here, but I'm actually interested in the low degree projection of this. So empty set denotes the degree in terms of these sort of fantasy variables x, but I'm interested in the degree of dependence on the graph, which is different. So there's a trade-off, there's a playoff of two notions of low degree. Okay. All right. So I have 10 minutes. OK. So let me now write down the definition of this guy in terms of this function lambda that Aaron defined for us and this discrete Fourier analysis setup. And then I'm going to say something quite briefly about how one analyzes these moment matrices. So what are the proof techniques in the literature? And then I think we'll be out of time. So now we can get a bit more formal about M. So what does it mean to take the low degree projection of some function? So let's think about a particular entry of this matrix ST. So lambda ST. Well, by what we just said, so OK, from this line down, capital N is always equal to little n choose 2. And capital lambda ST, we know just generically that it has a Fourier expansion. So it's equal to the sum over alpha. And these are subsets of n choose 2. Lambda hat ST at alpha times the character for alpha. And now MST of G will just be equal to this sum where I sum only over the low degree monomials. So here I'm going to say the degree of alpha is at most capital D. I'm going to move in just a second, sorry. Lambda hat ST alpha chi alpha of G. Okay, so this is it's almost the most explicit expression that we're going to get. And now the last thing I want to do is give you an idea of what these things look like and why. This is some funny looking function, but in some sense the function is defined to be able to compute these numbers. So I'm going to show you that there's a very easy computation of these numbers. Okay, and this is true in planted clique, but it's also true kind of across all of the problems where this technology gets used. I want to leave this up, so let me get rid of this. Sorry, tweeters. Okay, so I want to give you some idea of why these numbers actually turn out to be very nice, even though we went through some relatively convoluted path to get here. So I'm just going to look at the definition of this thing, lambda hat st of alpha. Well, by definition of a Fourier coefficient, this is the expectation under g sampled from gn half, that's our uniform distribution on a hypercube, of lambda st of g times the character alpha. And now let's use the definition of lambda. This is the expectation under g from gn half and 1/2. The relative density of g under the planted distribution with respect to the random distribution times the expectation of possible cliques in the graph G times this thing chi alpha. So I just expanded this definition. And now I'm going to use the definition of relative density to swap out these underlying distributions, right? So what does a relative density do? It just lets you say that this is by definition equal to the expectation under a graph sampled from this planted clique distribution. So now these graphs have honest-to-God cliques in them of, and let's see. So I should say that a pair xg was sampled from the planted distribution. So x is the indicator vector of this large clique. G is a graph with an honest-to-God large clique in it. xs, xt times chi alpha of g. OK, so now from here, I'm not going to carry out the rest of this computation because I don't have much time. But the point is that the definition of this function in terms of a relative density allows for very straightforward computation of these Fourier coefficients. Right? So at this point, it's like a very straightforward combinatorial calculation. You have an explicit expression for this thing. You have an explicit expression for this thing. You know how to sample graphs from this distribution. Aaron told you how, and you can just evaluate this. And it turns out, to cut to the chase, that it's equal to the size of the clique divided by n to the number of vertices in the combined sets alpha, s, and t. You can do that calculation on your own time. OK, in the remaining 2 minutes, and then I want to stop for questions, I want to say something about what kind of techniques are used to analyze these pseudo-calibrated pseudo-distributions in the literature. As far as I know, there are sort of 2 techniques that we know to analyze these things. And it would be nice if there were a more unified approach. Both of the techniques, OK, so as we said, the main difficulty is showing some PSDness, some positivity of these matrices. Right? Showing that they satisfy linear constraints turns out to be not very difficult. The main difficulty is to show that with high probability, M of G is a positive matrix. Okay? And we sort of know 2 techniques for this. But both of the techniques, maybe so there are some more experts on the CSP technique than I am in the audience for sure. But I think that both techniques you can ultimately view as producing some kind of Cholesky decomposition of this moment matrix, where the Cholesky decomposition itself depends on the graph, or on the instance in the case of CSPs. Right? So what we would like, I think what all of these techniques eventually do, is they construct some other matrix functions, I'm just going to say L of G and Q of G, such that M approximately factorizes in some Cholesky-ish way as L of G times Q of G times L of G transpose. And Q is roughly a diagonal BSD matrix. So somehow analyzing the eigenvalues of M directly is very difficult. One wants to get your hands on kind of a diagonal matrix, because then the eigenvalues are just explicit numbers that you have your hands on. And you sort of you do this, but you do this in a way that you keep the dependence on the instance present at all times. So you construct some kind of symbolic factorization. And all I can say is that the techniques for doing this, they seem right now to differ fairly greatly between planted clique style problems, by which I mean problems where one is interested in kind of dense inputs, like g(n)½ is a dense graph, and CSPs. So there are many authors of these papers are in the audience, and you can talk to them at the break. Yeah, I think that's the last thing I want to say. So we have 2 minutes, which we'll reserve for questions. Yeah. Oh, thanks. And thanks to Aaron. Yeah, Jess.
Yeah, sorry. Is the g in chi alpha of g the same g that you're taking the expectation over, or is that?
That's right. Yes. So
then where is the dependence on the actual instance?
Where's the dependence on the instance? So here I'm telling you a number. It's an actual real number. And the dependence on the instance is that this eventual moment matrix that you'll construct it's a low degree polynomial in the graph. These numbers are the coefficients of that low degree polynomial. And these characters carry the dependence on the instance. Yeah?
Can you say a little bit about the trade-off between the big D that you use to project and the...
Yeah, so somehow that's like the key thing that we're hiding here. Choosing this big D, so okay, let's say a few general things. So first of all, if I chose D to be, capital N, then I would just get this function back and I wouldn't have made any progress, right? So I better not do that. On the other hand, if I choose D to be 0, then I get the expectation under I of this function, which is nice in PSD, but it doesn't turn out to set, like I've lost all the dependence on the instance, right? So I can't possibly satisfy all of the constraints of the SDP. So I need to do something in between. And it's really non-trivial that choosing some D in between gets you something positive semi-definite. This is why we go through all of this trouble. It turns out that generally, I think you should take, let's see, capital D should be roughly little d times log of n for dense problems. And capital D should be about some large constant times little d for sparse problems. This actually brings me to a point that I wasn't able to address in the talk, which is that, so okay, up to this log, which is not that terribly important, the point is big D is like a little bit bigger than little d, but not that much. It's not asymptotically very much larger. One thing I want to address is that you can, without going through the pain of analyzing these moment matrices, you can make an remarkably accurate prediction for when they're going to be positive semi-definite just by choosing the appropriate D according to some rule like this, and then inspecting how well behaved individual entries of these matrices are. So once an individual entry has, say, a variance which is vastly larger than a diagonal entry of the matrix, basically you're just screwed, right? This matrix is not going to be PSD once some off-diagonal entry's variance is overwhelming the behavior on the diagonal. So that's an easy computation to do. You know this explicit polynomial, you can compute its variance, you can see what happens in the diagonal, it's easy to compare these things. And it turns out to be true for every planted problem that I know, that as soon as the variance of these off-diagonal entries becomes smaller than what mass you have on the diagonal, then the matrices become positive semi-definite. So there's some very easy, once you know this degree, you just write out the darn polynomial, compute some variances of entries on the off-diagonal, and you get a prediction that seems to be always right about what the eventual sum of squares lower bound you're going to be able to prove is. Yeah?
So I imagine that, the matrices aren't going to be exactly what you want. You're going to have to tweak them a little bit.
You mean which matrix? Like these thingies or these thingies?
The actual M.
This M guy?
Yeah. In particular, why does it satisfy exactly, the fact that if there are no edges in
Yeah. Great question. Okay, so 2 answers. Answer number 1 is that let's pop out of this planted clique example. So in the case of planted clique, you have to be slightly clever. A small tweak is needed. You're exactly right. If it were the case that the constraints of the SDP did not depend on the instance, and this is true for constraint satisfaction problems, for example, right? There you just want something to be Boolean, then it'll actually satisfy it for free. If you have constraints whose dependence on the instance is low degree, so what does this mean? The constraints of the planted clique SDP, they depend only on size little d neighborhoods of the graph, right, which is some sort of low degree function of the graph. Then you can make some kind of similarly low degree modification to this M, which will basically ensure that it satisfies those constraints exactly.
Sam, that's also the issue in CSPs, by the way, because CSPs, we want to satisfy the clauses exactly, which means they are constraints that depend on the instance.
Sorry. So if you, right, there are a couple of versions of CSPs. If you do CSPs where you put the clauses all in the objective function, then this is not a worry. You can also do a stronger version of a CSP's semi-definite program where you add them as kind of bigger families of constraints. And then you have this same issue that you need to make some little tweaks to M. Somehow these tweaks turn out to occur like, you can think of the tweaks occurring as very far out in this sum. So you only need to modify alphas that are very close to this big D. And I didn't, we saw this example where the magnitude of these coefficients decays exponentially. And what that means is that making small modifications out at the end of this capital D makes like the norm of the change that you make is really tiny.
Oh, yeah.
One last question.
Yeah.
So it's understandable that, for example, what you say is that for SoS large gaps, it's better to look at the moment side because you guess a bad solution, right? Not
yes.
An almost optimal solution of your SDP gives a bad value.
Yes.
Whereas if you add a small gap, for a problem with small gap, it's better to look at SoS certificates, right?
Yes, we think so.
So the moment side is better for large gaps, and the SoS would be better for the small gaps, right?
I think that's true. If you just want to prove small gaps, I agree that you want to study the proofs, the SoS proof side. When you eventually give algorithms, so not just proving small integrality gaps, but eventually you want to extract integral solutions, then the things that we know how to do tend to work simultaneously in the primal and the dual. So they often construct some SoS proof and then use that SoS proof to design a rounding algorithm in the moment matrix side. Does that make sense? Yeah. But there is there are examples. For example, there's this series of work on unique games and max cut worst case integrality gaps, in which the whole arguments take place in the SoS proof side. And you're showing that for particular interesting unique games instances or max cut instances that there exists a low degree SoS proofs that certify optimal values for these instances. That's sort of the small gaps literature I'm most familiar with. OK, thank you all.
Thanks, Sam. There'll be a sign-up sheet for the open problem session that's happening tomorrow.